Okay, in the last section, we talked about how do you handle doing a hypothesis test or doing inference on two populations where the samples that you're taking are dependent upon each other. In other words, there was a way of matching up our data points. We could either do pairs or matches, or we had before and after, or with or without some language like that. Now we're going to talk about what happens if I'm taking samples from two different populations and they are not related to each other or they are independent of each other. So what we need to talk about in this section is how to test a hypothesis regarding the difference of two independent means. And for that, we're going to use what's called Welch's t-distribution. It has some underlying assumptions. One is that the two populations I'm working with are normal. They have an unknown mean and standard deviation. So population 1 has unknown mean 1, mu1, and unknown standard deviation, sigma 1. The second population has unknown mean mu2 and unknown standard deviation, sigma 2. We're going to let n1 be the sample size from population 1 and n2 the sample size from population 2. If these are the underlying populations are normally distributed or the sample sizes are sufficiently large, then we come up with a new test statistic, t equals x1 bar minus x2 bar minus mu1 minus mu2 over the square root of s1 squared over n1 plus s2 squared over n2. It's approximately normal, or excuse me, it's approximately a student's t-distribution, and the degrees of freedom are the smaller of n1 minus 1 or n2 minus 2. So the process that we're going to go through here is going to be exactly the same as the one sample mean that we did before and the dependent samples that we did previously as well. The new thing that's going to happen here is how we calculate our test statistic. We will have a different formula for the test statistic. So if we want to test the hypothesis regarding the difference of two independent means, then we do have some assumptions we need to worry about. One, that the samples are independent, that we have randomly obtained those samples, and that the populations from which the samples are drawn are normally distributed or my sample sizes are large, and that the sample size is no more than 5% of the population size. Again, these are kind of standard assumptions that we've seen throughout of random samples, independent within each sample, and they come from a normal population, and we don't use too much of the population. We still have the same three hypotheses that we had in the previous section, or the three possibilities. We're either going to have that the two means are the same, or they're going to be different. So the null hypothesis is, again, always an equal statement, that mu1 is equal to mu2. The alternative will be dictated by what specifically we're interested in. If we're just wanting to know if they're different, then I'll use mu1 is not mu2. If I think the population from the first one has a smaller mean than the second, I'll use mu1 less than mu2. And if I think that the first population has a higher average, I'll use mu1 greater than mu2. So again, it's kind of the same three setup that we had before. The first thing is always an equality statement for the null hypothesis, and the alternative is either not equal, less than, or greater than, dictated by the wording of the problem. The second step is also the same as what we've previously done. We have to pick a level of significance alpha. So we're going to pick the level of type 1 error we're willing to make. The third step is the same stepwise, is in that we're going to calculate a test statistic. The new aspect of it is that we're calculating a test statistic using this Welch's formula. So x1 bar minus x2 bar minus the difference of the means over the square root of this s1 squared over n1 plus s2 squared over n2. We'll then determine the degrees of freedom. In the previous cases, we just had to take the number of data points minus 1 or the number of pairs minus 1. Here, we could have different sample sizes because the samples are independent, so our degrees of freedom will be the smaller of n1 minus 1 or n2 minus 1. We have the same pictures as we had before now, though. If it's a two-sided test, I can either go too far out to the right or too far out to the left. If it's a left-tailed test, I'm only worried about going too far out to the left. If it's a right-tailed test, I'm only worried about going too far out to the right. We'll reject the null hypothesis in a two-tailed test if we either move too far to the left or too far to the right. In a left-tailed test, we will reject the null hypothesis if the test statistics that we've calculated is too far to the left. In a right-tailed test, we will reject the null hypothesis if the test statistic we calculated is too far to the right. For the p-value approach, again, the same thing, except we have to calculate a test statistic using a slightly different formula. We're still going to take that test statistic and the number of degrees of freedom that we have and find that value in a table so we can determine what p-value is associated with that test statistic. If it's a two-sided test, we'll find the p-value and double it. If it's a one-sided test, we'll just find the p-value, and that will be our overall probability of observing the samples that we did, given that the null hypothesis was true. We can also use our StatCrunch or Minitab or graphing calculator to calculate the p-value for us. But the result is still the same. If the p-value is less than alpha, we're going to reject the null hypothesis. So again, notice we went through exactly the same steps as we did in the previous two methods. The only difference is the test statistic that we've utilized to make that decision. Based off of either our comparison to the critical value or a p-value, we will state a conclusion. Again, this procedure is robust in that minor departures from normality will not adversely affect the results. However, if the populations are far from being normal, then we may need to look for a different procedure. So let's do an example. We wanted to know whether or not state quarters had a weight that is more than traditional quarters. And we took two samples. We took 18 state quarters and 16 traditional quarters, weighing each of them and obtaining some data. Here it is in these two tables. We want to test the claim that the state quarters have a mean weight that is more than traditional quarters at the alpha's 0.05 level. Again, we set that level of significance. 0.05 is traditionally the level that is most commonly used. We should also check the assumptions that the populations are approximately normal, and if you do a plot, you can see that they are normal enough for us to utilize this method. When we give you a problem on the homework or on the exam, you will assume that it meets the underlying assumptions. When you get out and you're applying this in practice, you should make sure that you check those assumptions. And they're roughly nicely shaped. There's not really any outliers, so we can be confident that this method will be utilized correctly. Our null hypothesis is that there is no difference in the weights of the two quarters. The alternative is that state quarters weigh more than traditional quarters, so mu1 is greater than mu2. You might also want to modify the notation a little bit to make the subscripts have meaning. Either somewhere on your paper, as you're doing it, make a note of which thing is population 1 and which is population 2, or use it in the subscripts. So instead of maybe saying mu sub 1, I might say mu sub state. And instead of doing mu sub 2, I might do mu sub traditional. So that when I write the statement over here in the alternative, that the state average is greater than the traditional average. So that would be mu sub state is greater than mu sub traditional. We've selected our level of significance of 0.05. We will plug it now into our test statistic of x1 bar minus x2 bar over the square root of s1 squared over n1 plus s2 squared over n2. One question I have to think about is our formula had mu1 minus mu2 on it. Why isn't that showing up in what we had on our test statistic? Well, our null assumption is that these two things are the same. So mu1 minus mu2 is going to equal 0. So when we come down to do the calculation, this is really x1 bar minus x2 bar minus 0 because mu1 and mu2 are assumed to be the same. So we really are plugging things into that. We now have a test statistic of 2.53. We had 18 observations in sample 1, leading to 17 degrees of freedom, and 16 observations in sample 2, leading to 15 degrees of freedom. For this test, we will use the smaller of n1 minus n1 or n2 minus 1, which means we'll use the smaller of 15 or 17 as our degrees of freedom. So we will use 15 degrees. So to get the critical value, I'm going to go to my t-table. I'm going to go to the 15 row. I am going to go to the 0.05 column. And I'll see 1.753. Again, why didn't I use 0.025? Well, this was a one-sided test, so we were putting all of the probability in one tail, so that we used the 0.05 column. So our critical value is 1.753. So our critical region is anything above 1.753 steps above 0. We went up 2.53 steps, which means we went further out to the right than we're allowed. So we would reject the null hypothesis. We would then conclude that the average state quarter weighs more than the average traditional quarter. Again, since our test statistic is bigger than the critical value, we reject the null hypothesis. For the p-value approach, we would again go back to our table. We would go to our 15 row. We would look for where we saw 2.53. Well, that's somewhere between these two values. So we know that the p-value is somewhere between 0.01 and 0.025. And so we would know that the p-value is somewhere between 0.01 and 0.025. It's much closer to the 0.01 than it is the 0.025 because 2.53 is closer to the t-value we would have at 0.01. Either way, the p-value is much less than 0.05, so we will reject the null hypothesis. So there is sufficient evidence to conclude that state quarters weigh more than traditional quarters. Well, the last thing I want to talk about is briefly what happens if we have equal variances. The first one was just we had two normal populations. We didn't know anything about the standard deviations. What if, though, the standard deviations are equal? In other words, not only do we think that the averages might be the same, but we think that the two populations are really the same population, so that they have the same variances. We can actually do a little stronger test with this, and it's called the pooled t-test. The test statistic uses the same information we had before, except on the bottom we now have a pooled estimate of variation. And that pooled estimate is a weighted average of the two variances for the samples. Why are we doing this? Well, if they're the same population, both S1 and S2 are estimates of the standard deviation of the combined population. So this is just taking a weighted average of that information to come up with an overall estimate of the standard deviation of the population. And now this follows a student's t-distribution with n1 plus n2 minus 2 degrees of freedom. You will not have any homework problems that require to utilize this formula, but I wanted to bring up this idea because it will kind of surface again later when we talk about analysis of variance. And to let you know that as our assumptions change, we may have to modify our test statistic to accommodate those changes in assumption. So if we change the assumption from unknown variances to equal variances, or unknown standard deviations to equal standard deviations, we can come up with a stronger test that uses a different test statistic. What you will need to utilize in this section and in this class, though, will be the traditional Welch's formula of t sub 0 equals x1 bar minus x2 bar minus mu1 minus mu2 over the square root of s1 squared over n1 plus s2 squared over n2. This completes our discussion of how to find or how to do inference on two samples.